Okay, so this is Chemistry 108, Chemical Principles 1 at York College. We are continuing in Chapter 2. Last time we looked at this slide here, right? We looked at elements, molecules, and a few cases where we have atoms of an element, we have molecules of a compound, and we have, in some cases, we have molecules of an element, right, where we have, and you can see kind of from the schematics here what we're looking at, right? An atom is represented by a sphere, right? A compound is two different types of atoms joined together. Here you have one purple atom and three green atoms joined together in one molecule. Here you have molecules of an element. It's a molecule because you have more than one atom put together, but it's still an element because they're the same type of atom. Right? So two blue atoms make a blue molecule, a blue 2 molecule. We're going to take a more in-depth look at atoms, molecules, what's called atomic theory through the next couple of hours. And so here we have some common elements. You don't have to write these down. They're sort of, you'll become familiar with them as we go through chemistry. Right? Some of them you might have heard of, some of them you might not have. One thing you will notice is that elements are associated with an abbreviation or a symbol. So for example, carbon has the abbreviation C, sulfur has the abbreviation S. Right? What about silicon? Well, silicon couldn't also be S because it was already taken for sulfur. So silicon becomes Si. There's a bunch that are one letter. There are a bunch that are two letters, like helium is He, chlorine is Cl, calcium is Ca. And then there's some that don't seem to make any immediate sense at all. So iron, for example, is Fe. The lead is Pb. Mercury is Hg. These element symbols that don't match up with the name or don't match up with the English name, these are generally elements that were studied long, long ago, right? And so hundreds and hundreds of years ago, where the common language, or the language that kind of went across the scholarly language, was Latin. And so these are all Latin names, like ferrum is Latin for iron. So iron is Fe. Plumbum is Latin for lead. It's Pb, which is incidentally where we get plumber from. Plumber would use lead way back in their work, and so on. Silver, sodium, tin, and so on. Okay, so some common molecules. Again, you don't need to write this down, but you can kind of see these are actually all quite simple molecules. You have oxygen, water, carbon dioxide, ethanol. Maybe you feel very good about that. Maybe you don't feel so good about the ethanol the next day. You need some aspirin, right? And they get progressively more and more complicated. Okay, so we saw this last time, right? Two views of the world, the big, the very, very small. The big we think about like water like this, right? Macroscopic water is something that's liquid and clear and you drink. The very, very small water is something like this. It's a molecule that's made up of one oxygen atom and two hydrogen atoms. Same water, different ways of looking at it, different ways of thinking about it. Atoms and molecules, we made the point, they're way too small to see by normal means. And because we can't see them, but because we are a visual people, right? We like to visualize things in order to understand them, we come up with lots and lots of different models to explain what atoms and molecules are like. Right? None of these models are actually exactly what they're like. They are what they are. You can't see them, you can't tell. but the models explain different aspects of them and are useful for our understanding of how atoms and molecules, and therefore how matter, behaves. So we saw this a couple of weeks ago, states of matter, right? Solid, liquid, gas. So that solid, specific shape, definite volume. Liquid, no specific shape, definite volume. Gas, no specific shape, no defined volume. Gas expands to fill the container, and so on. This is from a macroscopic point of view. Right? So this is a piece of ice. Ice that has a specific shape. It's shaped like an iceberg and has a specific volume. What about solid, liquid, and gas from the submicroscopic point of view, from the what we would consider a molecular point of view? Here we have solid, liquid, and gas. So you may recognize this as the water molecule from about 2 or 3 slides ago. Gas is gas because the molecules have particular characteristics about them. Right? Gas molecules are, I didn't do it. Gas molecules are spread far apart. And because they're spread far apart, they don't really talk to each other. They don't really interact with each other. So if this gas molecule wants to go off this direction, it can do that. And if this gas molecule wants to go off in that direction, it can do that. And this one wants to go into the room, it can do that. That's why gases expand to fill the container. Liquids, however, in liquids, however, the molecules are much closer together. But they are kind of oriented in all sorts of different directions. Because they're close together, they are able to talk to each other. They're able to interact with each other. They pull on each other. And so if I pour the liquid out, it doesn't expand to fill the room. It just kind of puddles together. And so the water molecules stay together, but because they're disorganized, they're able to flow. They can kind of move. They can kind of roll over each other. Solid, we've had far too much solid water recently. Solid water is the same water molecules, but they're organized. They're close together and they're organized in very discrete ways. And the organization makes it really hard for those molecules to move. They kind of bounce around, vibrate in place, but they don't roll over each other. They don't spread. They don't expand. And what is solid water? Solid water is like ice, right? Ice and ice, of course, you try to pour ice, it doesn't pour. It just stays a block of ice. So you have solid. And so that, from the submicroscopic or the atomic or the molecular point of view, that's what water looks like in its different states. Okay, what about these other things, right? We looked at pure substances versus mixtures, right? This is from, again, what you've seen a couple of weeks ago. In the orange, you have the macroscopic. Now in the green, you have the submicroscopic, right? A pure substance is made up of one type of atom or one type of molecule.
So, even if that molecule has different atoms, it's still a pure substance?
Correct. So water has hydrogen and oxygen, right? But as long as, but that's different from hydrogen by itself and oxygen by itself, right? As long as it has just these water molecules, it's a pure substance. Those would both be pure substances, and those would be both be, if they were by themselves, and they would both be different pure substances. Right? Carbon dioxide is not particularly good for you, right? But it's a waste, a respiratory waste product. But it's in the air. We can have, we have significant amounts of carbon dioxide. We breathe it in, we breathe it out, no problem. Carbon monoxide is a different story, right? You have a bunch of carbon dioxide, you go real quick. So here's an example, right? This is a pure substance. Even though each one of these has two different types of atoms in it, they're each the same, right? Each molecule is the same. A mixture has more than one type of atom or molecule. And so here are two different types of mixtures. Here you have a mixture of blue-blue and blue-red. Here you have a mixture of just blue atoms and blue-red molecules. Each one of these has two different types of, in this case, two different types of molecules. Here, one type of atom, one type of molecule. Questions thus far? Okay. So we're going to revisit some of our properties, right? Not all of them, but some of them here. We have mass, volume, density, melt, blah, blah, blah. From the macroscopic point of view, remember we looked at physical properties and chemical properties, right? Physical properties are those that are measured without changing their identity or composition. Chemical properties have to do with how a substance reacts with other substances. Right? We saw these definitions again a couple of weeks ago. That's from the macroscopic point of view. What about from the submicroscopic point of view? Physical properties are measured or without changing the atomic arrangement. Right? We don't change how those little spheres are connected or not connected with one another. If I take a mass, I just take whatever I'm like to take a mass of and drop it on a scale, drop it on a balance. Same with any of these, right? Volume, you probably measured volume in the lab. You drop like a rock or something into a graduated cylinder, you see the volume go up. Right? The amount the volume goes up is the volume of your rock. Mass divided by volume gives you density, right? Melting and boiling points, you can measure that without changing the arrangement of the atoms, right? So when you have solid water and liquid water, you can, and you raise the temperature from, if you have solid water, you raise the temperature to get liquid water, you haven't changed the water. The water is still water. Okay, so what about the submicroscopic for chemical properties? They involve changes in atomic arrangement. And so therefore they're called chemical changes. So you burn something, we'll see, we'll look at combustion reactions. You burn something, what you do is you react it, you react the substance, the fuel, with oxygen, and you get, at the end, different products, right? You get some water, you get some carbon dioxide, maybe you get some ash, right? Which are all very different from what you started with. Same with acidity. We'll see in about chapter 4, acids react with bases to give you things that are neither acid nor base. By definition, yes. So combustion is the reaction of a fuel with oxygen and to produce heat plus some particular products. Other questions? Okay, so here's the point again. Physical changes, no change in connection between atoms. Phase changes, changing from solid to liquid to gas. You don't change the connection between the atoms in the molecule, right? Each one of these molecules is still one red connected to two whites. Here, one red connected to two whites, even though they're arranged in a particular way. So change of state is a physical change. Okay, so what about water, right? So if we heat water, we boil it, no change between the connections, no change between the connections in the atoms in the molecule. But if we do something like this, right, we take water and we run an electrical current through it, then we're going to get some changes, right? If you do take water and you run a current through it, you're going to break the water down into oxygen gas, O2, and hydrogen gas, H2. That is a chemical change. The water that you start with has one oxygen and 2 hydrogens. What you get at the end is 2 oxygen, O2, and hydrogen, H2. The atoms have rearranged themselves. And they're quite different now. Questions? Okay. So we've kind of connected chapter 1 with chapter 2. Now we're going to take a kind of deeper look at atoms, right, and what's called atomic theory. And atomic theory is quite remarkable. It was developed by Dalton, right, John Dalton, way back in the early 1800s. And what's remarkable about it is that Dalton discovered or uncovered all these things that we know now are basically true without the benefit of, say, electricity, right? And some really basic things that we take for granted. So Dalton's atomic theory, he developed these things largely by just mixing stuff, reacting them, heating them, looking at masses before and after. Every element is composed of extremely small particles called atoms. We've kind of made this assumption when we're talking about stuff so far. And now we're kind of codifying it. Now we're making it sort of official. All atoms of a given element are the same as one another, right? All oxygen atoms are the same. All iron atoms are the same. And oxygen and iron are different, right? They're different from atoms of other elements in mass and in other properties. Atoms are not created, not destroyed, and not changed into other types of atoms during chemical reactions. So if you start with oxygen in your H2O, after your chemical reaction, you must have oxygen, perhaps in some other form, but also you still must have your oxygen atoms. So if the atoms are not created, destroyed, or changed, how do the changes come about? They come about from how the elements or from how the atoms combine with one another. So compounds are formed when atoms of more than one element combine. A given compound always has the same types and relative amounts of atoms. So water always has 1 oxygen, 2 hydrogens. It doesn't matter if it's water from my bottle or water from the tap, water from the ocean. Right? Water always has the same composition. So this is the theory, right? The theory is basically Dalton did a bunch of experiments and he made some conclusions, right? And he developed a model that seemed to explain the results of his experiments. Now, other people have done further experiments after Dalton, which tell us more about atoms, and we'll get into some of them. Okay, so I'm going to move on. Don't worry, this slide is coming back, and it's also going to be on Blackboard. So based on these 4 points, these 4 tenets of atomic theory, we get a number of laws. Right? And laws are a little bit different from theory. Laws are observations that are made over and over and over, right? And they're always repeatable and they never change. So the law of conservation of mass says that the total mass, the total amount of matter before and after the chemical reaction is the same. So this is the reverse reaction of what we saw, of the electrolysis reaction we saw, where water was broken down into hydrogen and oxygen. Here we have hydrogen, this is a combustion reaction, being burned in the presence of oxygen to give me water. And so if I have a certain mass of hydrogen and react it with a certain amount of oxygen, if I have no leftovers, if I have no leftover hydrogen and no leftover oxygen, then the mass of what I started with and the mass of the water I get at the end have to be the same. Total mass of the matter before and after a chemical reaction is the same. So where does that come from? That comes from this. Right? Atoms are not created or destroyed or changed into other type of atoms. And kind of from here too, right? Atoms are identical to one another and different from atoms of other elements. Right? So if I have oxygen atoms and hydrogen atoms in the beginning, and I have oxygen atoms and hydrogen atoms at the end, and I have the same amount because they're not created or destroyed, and there's no other elements because they're not changed, what I start with, however much material in grams I start with in the beginning, I have to have at the end. So another law, the law of constant composition. In a given compound, the type and relative numbers of atoms are always the same. Right? So water always has two hydrogen atoms and one oxygen atom. Ethanol always has 2 carbon atoms, 6 hydrogen atoms, 1 oxygen atom. Right? And this comes basically also from those 4 points. This comes from essentially point 3 and point 4. So again, ethanol, regardless of the source, is always going to have 2 carbons, 6 hydrogens, and 1 oxygen, whether you get the ethanol from the lab or whether you get the ethanol from the bar, right? Just as a side note, right, the ethanol that you may use in the lab is not something you want to drink. So don't get any ideas, because they put very, very small amounts of, because basically you need particular licenses to sell drinking alcohol, right? And they put very, very small amounts of very, very poisonous materials in the lab alcohol, so you don't drink it. So don't try it. The law of conservation of mass. Right. Total mass of matter before or after a chemical reaction is the same. So that's the first law. The second law is going to be the law of constant composition, right? And that comes basically from here, right? If you put these two together, compounds are formed when atoms of more than one element combine. A given compound always has the same types and relative amounts of atoms. And so these 4 points, actually, if you look in your book, they're there. The wording may be slightly different, right? I've tried to make it so that, we can highlight these kind of bullet points to get to the kind of guts of them. The ideas are the same. And the law of multiple proportions. This is kind of a little bit harder to understand, but not so hard to understand once you see the examples. I think that's something that occurs commonly in chemistry. Right? You have, we'll often put up a definition. You'll read the definition, you'll say, I know those words, but they're not making any sense. Don't freak out, because very often once you see the examples, or once you see the explanation, then it starts to make sense. So here's an example, I think, of that. Law of multiple proportions says something like this. When you have two elements, element A and element B, when they combine to form a compound, their masses, the masses of A and the mass of B, will always be small whole number ratios. They can be different ratios. For example, carbon dioxide and carbon monoxide. So here's one example, right? So here's your what we saw in the law of conservation of mass. When you're forming water, the ratio of hydrogen to oxygen is 1 to 8. Right, in terms of the mass, right? 1 gram hydrogen, 8 grams oxygen. Now, there's another compound that contains only hydrogen and oxygen, and that's called hydrogen peroxide. Does anybody know what hydrogen peroxide is used for? Sorry? Cuts or bruises, right. So hydrogen peroxide is used basically as a topical antiseptic. It's used to kill germs. Any other uses for hydrogen peroxide that anyone knows of?
Hair bleach?
Hair bleach, right. So peroxide is also used to lighten hair, hair color. And if and when you go on and take organic chemistry, you'll learn why peroxide is good for both of those things. Right? Peroxide basically reacts with, is a very reactive substance, reacts with particular types of bonds, which both can kill things, kill germs, and can also change colors. So hydrogen peroxide has this type of structure. It's H2O2. You have 2 oxygens and 2 hydrogens, all connected in one molecule. And in order to get that, you need, okay, something's not right here. Okay, the colors are all mixed up, but that's okay. You need 16 grams of oxygen and 1 gram of hydrogen, right? You need, because this is H2O, this is H2O2. So what do you have? You have twice as much oxygen relative to the hydrogen. So you have 16 grams of oxygen, 1 gram of hydrogen. So the ratio of H2O and O2 in peroxide is not 1 to 8, it's 1 to 16. And so that's the small whole number ratios. And so the ratio of H2 to O2 is 1 to 8. Ratio of in water, peroxide is 1 to 16. That's not supposed to be there. 16 divided by 8 is 2. Right? There you go with your small whole number. Right, so peroxide contains twice as much oxygen relative to hydrogen. Another example that, oh good, some of you took your cards out. I like that. Those of you watching, you can't see what I just saw. Okay, so Mr. J, I remember his card, Agent J, asked about carbon dioxide and carbon monoxide. Right, here's another example of the law of multiple proportions. Right, carbon dioxide is CO2. Carbon monoxide is CO. Right, so where are these numbers coming from? These particular numbers, in terms of the masses, we don't know that yet. You'll learn that soon. But here you have 8 grams of oxygen for every 3 grams of carbon, and here you have 4 grams of oxygen for every 3 grams of carbon. 8 divided by 4 is also going to give you 2. What does that tell you? That tells you there's twice as much oxygen here as there is here. Again, okay. The 8 divided by 4 is going to give you 2. Carbon dioxide has twice as much oxygen as there is in carbon monoxide. The statement of the law of multiple proportions, it's a little bit convoluted, right? It's a little bit strange. Why is that? That's because when Dalton developed, and those who worked with him and followed him, developed these things, they didn't know this, right? They didn't know about like these kinds of like balls and sticks and bonds and stuff, they were figuring it out as they went along. And all they could see really was mass, right? That was their instrument of measuring things, pretty much was a balance, right? And so they state this in terms of mass, right? Once you see it, you don't need to think about the mass so much. You can just say, oh, CO2, CO. One has 2 oxygens, one has 1 oxygen. Right? We have the benefit of 200 plus years of the development of chemistry. Right. Okay, so which of the following pairs are examples of the law of multiple proportions? Yes, no.
Yes.
Yes, why yes?
Because the second one has one more oxygen than
Right, because you have element A, element B, and different multiple, right, different proportions. What about this? H2SO3 and SO3. No, right, because you don't have the same elements. H2O, H2S, same idea, you don't have the same elements. What about CH4, C2H6? Yes, it's a little more complicated, but here you have a ratio of 1 to 4. Here you have a ratio of 2 to 6, which you can reduce to 1 to 3, right? So 1 to 4 and 1 to 3. More questions? Any other questions? Yes?
So the same, like, there's a compound that has 2 carbons and 6 hydrogens.
Yeah.
But they're bonded, there's 2 of them, but they're bonded differently. It creates something completely different. Even though they have the same amount of each element.
Yes, yes, that's that's a very interesting point, and that's a little more advanced than what we're coming to, right? So I think you don't have your card, so I forgot your name, but what your friend is saying is C2 and H6. If you kind of use your imagination, based on what you know now, which is not all that much chemistry, you can imagine, if you're using like Tinker Toys, you could put the C's and the H's in different, connect them in different ways. All of which would have 2 C's and 6 H's, right? Maybe you could have 2 C's and then HHHHHHH, or HHHC, HHHC. Those would be different compounds, but we don't know that yet. Okay, so these no, yeah, no, yes. Okay. And the law of multiple proportions can be derived from these two, right? Atoms are not created, changed, or destroyed, and when compounds are formed from more than one element, they have the same type and relative amounts of atoms. Okay, so right, and so those are the 4 points in the theory. These are the 3 laws. And just, in case you didn't get it all down. If you still didn't get it all down, well, they'll be on Blackboard. Okay, so we looked at atoms. We're going to take a closer look now at atoms. So far, this is how we've looked at atoms, right? We said atoms are these little spheres. And here's an atom of one type of element red, right? And you might have an element that's blue, and an element that's purple, and another one that's green. That's, not, that works, right? But there's more, much more than that when it comes to atoms. Wait, yeah. So these pages are wrong. They're a different edition of the book. So when people started thinking about atoms, they realized that there's 2 different types of atoms are made up of 2 different types of building blocks, and some of them are positively charged and some of them are negatively charged. Right? And this led people to start thinking. Remember, we said we can't see these atoms. So people start devising models to try to explain some of their properties. And because we're visual people, the models tend to be quite visual. J.J. Thomson, he was renowned for many things. He did a lot of studies on charged particles that come from atoms. He developed a technique called mass spectrometry, which still gets used today in various forms. But his famous model of the atom turned out to be quite incomplete or quite incorrect. It's correct in the fact that there are these two different types of characteristics that we term today or we know today are kind of positive charge and negative charge, but that's about all, right? So what his model was kind of nicknamed was a plum pudding model, right? And so there was, they were English, right, and British. And they had this dish where you had a pudding with lots of kind of goodies embedded in the pudding. And he said, okay, so let's imagine the atom as a positively charged sphere with negatively charged goodies embedded in them. Right? It turned out that that was quite not correct. And so I'm showing it to you, but don't remember too much about it. A little bit, right? Right. See, yeah, see. Rutherford, Ernest Rutherford, did another experiment, and your book talks about a bunch of other experiments. We're not going to go through all of them in class, but Rutherford did this experiment, which was quite interesting. So he used what's called alpha particles. Now, you don't know quite what this means yet, except they're positively charged. And he was able to shoot a beam of them. What he had here was a very, very thin foil made out of gold. And so if you considered the plum pudding model and you had atoms kind of like this, right, with the goodies embedded in them, and you shot a beam, what would happen? What would you expect? Well, I would expect that it wouldn't go through, right? It's kind of, you have basically a wall, and even if you only have a few atoms thick, what's going to happen? It's either going to get absorbed or it's going to get deflected. Yep.
Don't some go through and then some deflect and come back?
Well, that's because the plum pudding model was incorrect. You're correct. So what Rutherford did was he proved that this, which is this, was incorrect. And that's because what he saw was not that they didn't go through, but that most of them actually went straight through. Right? If you had a gold foil, a few layers of atoms thick, and most of these alpha particles went straight through. What does that mean? That means most of it's empty space, right? And they could just go straight through. And just a few of them, right? This is actually an exaggeration. Much, much fewer actually got scattered around the ring, right? So many of them went straight through, and a few of them got scattered. And so what's the implication there? The implication is it's mostly empty space, right? The ones that are going straight through are not encountering anything solid and substantial. And the very few that get scattered are basically being deflected or bouncing off of, you could think about it that way, or being deflected by something that is solid and substantial. And so the model that gets developed, that comes out of this, is this kind of model here. And it's the model that that we think about now. Right, so most of these, if here's your atom, right, these kind of tan spheres are your atom, these sort of darker orange spheres are what we call the nucleus. And the nucleus contains, depending on your type of atom, over 99.9% of the mass of the atom, but in a very small space. Right? So 99.9% of the mass is here. That means 0.1% or less is spread out all around here. Right? Not much there, right? And so when the alpha particle encounters the light beige part or the light tan part, what happens to it? Absolutely nothing. It just goes straight through. And most of them are just going straight through. But a few of them are going to bang, right, hit the very small nucleus and get deflected. And so it turned out that the nucleus, right, nucleus deflects the alpha particles, but collisions are rare. The electrons, the alpha particles pass right through. And that's what most of them encounter. It turned out that the nucleus was positively charged. The electrons were negatively charged. Questions here? Okay, so at this point it's 4:54 or so. So we'll take a 10-minute break and come back at 5:04. Okay, so we've established, based on Rutherford's experiment, this concept of a nuclear atom, right? That there's a nucleus and that there's kind of electrons around it. We're going to take a closer look at the nuclear atom. Here's the kind of Rutherford kind of nuclear ball. Now, some of you, probably most of you, if you've done, depending on how, or will or have, come up with atoms or come across atoms that look something like this, and then you have like circles and then circles around circles, something like that with electrons going around in circles. There's a certain amount of accuracy to that type of model, but there's also a whole bunch of inaccuracy in that type of model. So we're not really going to use this, right? The electrons, it turns out, don't really kind of like go around in circles like planets around the sun, which this kind of implies. What's much more accurate is that, well, here's your nucleus, and it has a positive charge, and around it there's kind of like a cloud of electrons. Right? The electrons don't actually go around and around in circles. They're kind of like they're a cloud. They kind of spread themselves around, and they kind of move in predefined or defined areas, but not like, right? They kind of, usually what we talk about is a cloud of electrons, right? And so in the nucleus you have a positive charge. In this kind of cloud around it you have electrons. The nucleus is made up of protons, which have a positive charge, and neutrons, which have no charge. And these are what are called subatomic particles. We kind of dig into the atom and kind of like blow it up and try to envision what it might kind of look like. Remember, we can't see these, right? So this is the models that we use, whether that one or this one, they're ways to explain things that we know. And one thing we know is that these are able to deflect alpha particles, and this is not. Why is that? Well, we'll see. So here we have our three what we call subatomic particles, right? Proton, neutron, and electron. And we said protons are positively charged, electrons are negatively charged, neutrons are neutral. And we assign to the proton a charge of +1, assign to the electron a charge of -1, assign to the neutron a charge of 0. Now, what about mass? Right, we said that 99.9% of the mass of an atom is in the nucleus. That is, in the protons and neutrons. So the mass of a proton, the mass of a neutron, they actually have masses that can be measured in grams. Right, that can be measured in grams. But for convenience sake, we don't use grams when we're talking about masses of elements and atoms or atoms and molecules and nuclei and protons and neutrons and electrons. We use a type of measurement called atomic mass units. And so we say a proton has a mass of 1, or about 1. A neutron has a mass of about 1. An electron, relative to the mass of a proton or a neutron, is really, really, really small. Small enough that for most intents and purposes, we can call it 0. And now when you get to ALEX, and in the very beginning, they'll ask you something about the actual mass of an electron. The actual mass of an electron relative to a proton or neutron is 0.00055. It's really, really small. And protons and neutrons are not exactly 1, but they're close enough to 1 that for many applications we just call them 1. Same with the charge, right? So charge, if you've taken physics, and if you go on and take Chem 2, we'll talk about charge in terms of coulombs, right? That's a real, actual metric SI value. And I think that's negative, 19. You don't need to know that number, right? So, and the mass of a proton, I think that's a typo there, so we'll cover that up. The mass of a proton is also very, very, very small. You don't need to know that number either. But what is it? It's 10 to the negative 24th grams, right? So that's 0.000024 zeros followed by this. And this is 10 to the negative 28th grams, right? So it's really, really small for electrons. Okay, so here's something you do need to know, right? The overall charge on an atom is going to be 0. Atoms are electrically neutral. So what does that mean? In an atom, you have the same number of protons and electrons. Because where does the positive charge come from? It comes from protons. The negative charge comes from electrons. So in order for that to add up to 0, if you have 5 protons, how many electrons do you need? You need 5 electrons.
So all atoms have a charge of 0?
Correct. So there are chemical species that don't have a charge of 0. Right? Those are species we would call ions. Right? But if we're talking about an atom, it's going to be a charge of 0. Right, again, so nucleus surrounding the nucleus. So let's think about how do we connect what we're learning here to what we've been talking about in terms of different elements and so on. Okay, so each element is going to have a few, or each atom of an element is going to have a couple of numbers attached to it. The atomic number is the total number of protons in an atom. And what's called the mass number is the total number of protons and neutrons. The atomic number defines what atom you're talking about, what element you're talking about. All right, and when you're looking at, so that's really small. Okay, so when you're looking at this periodic table, we'll talk more about the periodic table either later today or on Thursday. You start with hydrogen, which is 1, and then helium, which is 2, and then lithium, 3, 4, 5, 6. Those are the atomic numbers. Right, that's how many protons you have. Mass number is protons plus neutrons. Why is that? Because the mass is basically concentrated in the protons and the neutrons. The electrons are so light that they don't contribute that much. They don't contribute in any real appreciable way, in most applications, to the mass of the atom.
So mass number minus atomic number equals the number of neutrons?
Yep, that's right. Mass number minus atomic number equals the number of neutrons. So you'll be doing kind of calculations like that. We'll look at that. So a typical hydrogen atom. And a typical hydrogen atom has 1 proton, no neutrons, and 1 electron. So what's the atomic number? 1. And what's the mass number? The number of protons, which is 1, plus the number of neutrons, which is 0. 1 plus 0. You can use your calculator if you need it. Is going to be 1, right? So atomic number equals 1, mass number equals 1. We can abbreviate it like this, where H is the symbol of the element, hydrogen. The atomic number is 1, and the mass number is 1. So the mass number goes superscript to the left, the atomic number goes subscript.
So in isotopes, what changes atomic number and mass number?
You're getting ahead of us. We'll get there. So isotopes are the same thing. So the atomic number doesn't change. Same atom, same element, but the number of neutrons changes. We'll get there. So remember, it's a typical hydrogen atom, right? We would say this, or we could call this hydrogen 1, or we could call this 1H1. Technically speaking, we don't need to put this here. Why is that? Because hydrogen always has an atomic number of 1. The atomic number defines what type of element it is. Here's another view. The hydrogen atom has an atomic number of 1, a mass number of 1, 1 proton in the nucleus, and 1 electron that's kind of floating around somewhere here. Okay, so here's another example. Typical carbon atom has 6 protons, 6 neutrons, and 6 electrons. So what's the atomic number of this typical carbon atom? 6. What's the mass number? 12. Very good. And we could write this 12C6. Another way to call this would be carbon 12. Questions so far? Okay, and another view of this would be a symbol, atomic number, mass number. Another view of this we could look at like this, right? There's 6, charge of plus 6. In the nucleus we have 6 protons and 6 neutrons. And floating around in the electron cloud we have 6 electrons. So the carbon has, and we would call this 12C6. Okay, so isotopes. You'll notice we said a typical hydrogen atom and a typical carbon atom. Right? But there are different types of hydrogen atoms and different type of carbon atoms. So the identity of an element is determined by its atomic number, not by its mass number. So if it has 1 proton, it's always hydrogen. If it has 6 protons, it's always carbon. The number of neutrons might be able to vary. So for example, a typical hydrogen atom, we said, has 1, 0, and 1, atomic number 1, mass number 1. There are other types of hydrogen. One of them is called deuterium. Deuterium has how many protons? 1, because it's still hydrogen. But it has 1 neutron and 1 electron. Typical hydrogen has 0 neutrons. Deuterium has 1 neutron. So the atomic number of deuterium is 1. The mass number is 2. 1 plus 1. Okay, that phantom box keeps appearing. Stop it. Okay. So isotopes are atoms that have identical atomic numbers but different mass numbers. So hydrogen actually has 3 common isotopes. Regular hydrogen, deuterium, and tritium. So we looked at regular hydrogen, we looked at deuterium. Let's think about tritium. Tritium has how many, what's the atomic number? Right, atomic number equals 1. And the mass number? Sorry? Mass number equals 3. How many protons? 1 proton. How many neutrons? Right, 2 neutrons. You can do this. If it has 1 proton, it's hydrogen, regardless of whether it has 0 neutrons, 1 neutrons, 2 neutrons, or 370 neutrons. It doesn't really exist, but if it did, it would still be hydrogen. Okay, so same with carbon, right? There's several common isotopes of carbon. Carbon-12, carbon-13, carbon-14. Right? Carbon doesn't have these special names like deuterium and tritium, and most of the elements don't. Right? Many of the elements, I'm just showing you 2, right? Hydrogen and carbon. Many elements have more than 1 common isotopes. Most of them don't have special names. For hydrogen, they do. This we would call carbon-12, carbon-13, carbon-14. 6 plus 6 is 12, 6 plus 7 is 13, 6 plus 8 is 14. If it has 6 protons, it's carbon, regardless of whether it has 6 neutrons, 7 neutrons, 8 neutrons, or more neutrons, or fewer neutrons. Okay, we looked at atoms. Now we're going to look at a little bit at elements. Right, so way back in 1869, right, so Dalton, do you remember when Dalton developed the atomic theory? 1802, right, or 1802, 1803. This was 1869. And 2 chemists, Russian named Mendeleev, Dmitry Mendeleev, and German, I think, named Mayer, noticed that if you put, something's missing here. Where's the hydrogen? Oh, okay, no, the hydrogen's not there, okay. That if you ordered many of the elements according to they didn't know atomic number yet, right? They only knew weight, right? So if you ordered them by their weight, you started getting properties. Remember, we talked about properties of matter, properties that repeated. So here we have lithium, beryllium, boron, carbon, and so on. You don't need to copy this all down. And you put them kind of in order, and then what you would notice is you would see repeating properties. So all of these in purple are very soft reactive metals. Lithium for Li, sodium for Na, K for potassium. And that these red ones are harder metals. So beryllium and magnesium and calcium. And these are just some examples. These are called, and these guys, fluorine and chlorine, are nonmetals. They dissolve in water to form acids. We haven't talked about metals and nonmetals yet. And these are all gases, helium, neon, argon. And they don't react, at least in 1869, they didn't react with anything. And so this was called periodicity, right? Periodicity basically, or a period is basically something that repeats and repeats and repeats, right? And so the properties would repeat, and they noticed that the elements had these periodic properties. These folks started to put the elements into a table that becomes the periodic table of the elements. Now, what we know today is that the order really comes from the atomic number, not the mass number. And there are some cases where the mass, if you do it by the mass number, it doesn't work right. So atomic number is what we use today. And so the periodic table can come in many different views. Here's a very simple periodic table where all you have is the element, symbol, and the atomic number. And on the top you have, okay, so before we get to the top, you have going across what are called rows or periods, and going up and down, columns or groups are also families, called families because the properties are related. You'll notice that you have rows 1, 2, 3, 4, 5, 6, 7. Right, row 1 starts from the very top. And these families are also labeled, and they're labeled in different ways depending on sort of what brand and variety and age of periodic table you have. One way of labeling them is just 1 through 18. Right, so you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. The other way is to break them into the A groups and the B groups. Right, so here you have the B groups, and their numbering is kind of strange. We won't talk about that quite, we probably won't talk about that at all, but we will talk about the A groups, right? We go from 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Those are called main group elements. We'll deal a bit more with the main group elements than the B group elements. The B groups are called transition elements. And we'll also talk about them a little bit, particularly as we get to chapters like 7 and 8. Right now what we're doing is basically taking a little tour of the periodic table. Right? Because this is chemistry, this is kind of like your map, right? And so you need to know some things about it. And so we have columns, groups, or families, up and down. We have rows or period going across. In addition to your A group and your B group, you have what are called the lanthanides and the actinides. Right? The lanthanides are called lanthanides because the first element in the row is lanthanum. Actinides are called actinides because the first element in the row is called actinium. Right? And why are they out here? Well, they're out here because they really belong stuffed in here. And again, but if you did that, it would get really, really wide, really, really long. So, and we'll learn why, again, once we get about halfway through the semester. Okay, here's another view of the periodic table. Some of the families or some of the groups have common names. Right, we talked about group 1. Those are called alkali metals. Right, and they're alkali. They form alkali compounds or bases. Lithium, sodium, potassium, rubidium, cesium, and francium. Group 2A are called the alkaline earth metals. Group 6A are called the chalcogens, 7A halogens, 8A noble gases. Right? Those are common names that, if you take chemistry, and someone says something about a halogen, or you should be able to say, oh, I know what that's talking about. It's talking about group 7A. Someone says something about the noble gases, they're talking about group 8A. Okay, and I don't know how well you can see the color here, but you have maybe that's a little better. You have these different shades. You kind of have this tan, purple, and kind of light green. And you have different types of elements here. Right? In the tan, you have what are called metals. In the light green, you have what are called nonmetals. And in the purple, you have metalloids, also sometimes called semimetals. The metals are mostly all the elements here, right? Those are all in the tan. The metalloids live mostly along this staircase line over here, except for aluminum and polonium, which are considered metals. And the nonmetals, this little triangle over on the right. So what are, there's obviously, from what we're seeing here, many more metals than nonmetals. But before we think about, or we continue talking about those, what are some characteristics of metals? What is a metal? Right? We kind of know what metal is, right? But what makes a metal metal? What are some characteristics? Agent J. It's density. Not really. Some metals, like aluminum, are quite light, or quite not dense. Some are very heavy. Yes, Hakuna Matata. Yeah, so metals tend to be shiny, right? Yes. They conduct electricity. Any other thoughts? So metals are shiny. They conduct electricity. They conduct heat very well. And they're usually what we call malleable. That means if you pound on it, it's not going to break. It's going to flatten instead. And so what can you do with metal? You can kind of pound it and beat it into different shapes. Nonmetals, on the other hand, tend to not conduct electricity very well, not conduct heat, and in the solid form, if you hit it, they'll break. Metalloids, or semimetals, are kind of in between. So here's perhaps the most famous metalloid, Si. Do you remember what Si is? Silicon. So who knows an application of silicon? Very common. Most of you probably have one in your pocket or bag or something. Sorry? Not your phone case. Sorry? Oh, that's silicone. That's not exactly the same. But silicone probably contains silicon, right? But the element silicon is in the computer chip, right? That is in your computer or in your phone. Has anyone heard of a semiconductor? Right, so your computer chip is typically made out of silicon, and silicon is a semiconductor. In brief, what that means is that under some conditions it'll conduct electricity, under other conditions it won't. Right, and so what does that enable? If you can control that, then you can, start doing things like, under some conditions I want the electricity to flow that way, and that makes the screen this particular pixel turn blue. On other conditions, I want it to flow that way, conduct this way, not conduct that way, and that makes that pixel turn green, something like that. So semiconductors, because they are generally kind of tunable conductors, sometimes yes, sometimes no, they find their way into a lot of electronics like computer chips. Okay, so here's another view of the periodic table. Right, here's a blow up. You have the element, you have the name, the atomic number. This is not quite the mass number. This is what's called the average atomic mass. That's something we'll talk about in the next chapter. Related but not the same. Right, and so, yeah, that's what I mentioned before. Know the names and the symbols for elements 1 to 36. What does that mean? That means if you look at a periodic table, not like this that has the names on it, but like this, and I were to give you a test question that had the element Zn in it, you could figure out what's Zn. Zinc, right? Or if I said, we're going to talk about bromine, you'd be able to find bromine. Can you find bromine? What's its atomic number? 35. Right. So 1 to 36 plus whatever we talk about in class. Right? So if we never talk about like Re, rhenium, you don't need to know Re. But the ones that we use commonly in class, you'll need to know iodine. We'll talk about probably, some of them. So it sounds kind of daunting, but it's really not that daunting. Okay, so atoms and elements. Now we'll talk a little bit about molecules and compounds. Right? A lot of the rest of the class has to do with molecules and compounds. But we'll start here. Right, so molecules is putting the atoms together. And so what is a molecule? We've talked about molecules. We've thought about molecules in terms of these little spheres that kind of get connected. But formally speaking, what is a molecule? A molecule is an assembly of two or more tightly bound atoms that can behave as a single distinct object. So water is our kind of favorite molecule so far. It has 3 atoms, 1 oxygen and 2 hydrogens, that are tightly bound. And that water molecule doesn't behave like hydrogen. It doesn't behave like oxygen. It behaves like water, a single distinct object. And so a whole bunch of different molecules, right? Carbon dioxide, carbon monoxide, peroxide, we've met. A molecule can be, most of these are compounds. This oxygen is an element. It's O2, right? And so this is called a diatomic element, diatomic molecule. Diatomics are made up of 2 and only 2 atoms, and several elements exist as diatomics. We should know what they are. What are they? They're hydrogen, H2, and then the guys in this corner over here. These are the common diatomics. So H2 is hydrogen, N2, what do you think that is? Nitrogen, O2, oxygen, F2, Cl2, fluorine, Cl2, chlorine, Br2, bromine, I2. Okay, so you know the elements. You didn't even try that hard. Maybe you did, I don't know, when I wasn't looking. But those are common diatomics. You need to know what they are. If we talk about molecular oxygen, you need to know what we're talking about, O2, not O. Okay, so molecules, and we've kind of been doing this without formally introducing it. Now we're formally introducing it. Molecules have formulas, just like elements have symbols. Right? Molecules have formulas. We talk about water, and even people who don't know very much chemistry know that water is H2O. Right? Many people know that carbon dioxide is CO2. There's different types of formula, right? The molecular formula shows the actual number and types of atoms in a molecule. What does that mean? That means, stop. Okay. So that means water is H2O. It's a molecular formula. Hydrogen peroxide is H2O2. In a molecule of hydrogen peroxide, what you have is 2 oxygens and 2 hydrogens. So the molecular formula is H2O2. It shows the actual number and type, right? 2 oxygens, 2 hydrogens. Do I have time for this? Yeah. Okay, so there's this corny joke that goes like this, right? So a chemist and a philosophy major walk into a bar, right? And the chemist says, "I'll have H2O." And so the bartender gives him a glass of water. He drinks it, and he's all happy. Then the philosopher says, "Oh, that looked good. I think I want the same thing." So he tells the bartender, "I'll have H2O2." And so he drinks the H2O2 and he dies. Okay. The empirical formula is another type of formula that shows the relative number and type of atoms in a molecule in the smallest whole number ratio. The relative, instead of the actual, number and type of atoms in a molecule in the smallest whole number ratio. So H2O2, if we take a ratio of the hydrogen to the oxygen, well, it's 2 hydrogens to 2 oxygens, right? And so that would be 2 to 2. But is that the smallest or most reduced way to write that ratio? No, it's not. What is the most reduced way to write that ratio? It's 1 to 1. So for hydrogen peroxide, the molecular formula is H2O2 because it shows the actual number and type of atoms, but the empirical formula would just be HO. Why do we use empirical formulas? Okay, so often they're the same, but right, sometimes they're not. Well, let's take a step. Who knows what this word empirical means? Anyone haven't heard of this word before? Yeah. Not quite. It's a good thought based on the what we've been talking about. Empirical. Anybody? No. So empirical means there's some evidence for a conclusion, right? We might not understand why it happens, but we have some evidence. We did some experiments. We have something that kind of tangible that we can base our answer on. So why is this an empirical formula? Because there's some types of experiments that are done. We'll learn a little bit about this down the road. There's some types of experiments that are done that tell us the relative amounts of elements in a compound, right? So we might do an experiment that tells us there's 1 part hydrogen to 1 part oxygen, or there's a certain ratio of grams of hydrogen to grams of oxygen. That gives us the empirical formula, but what it doesn't tell us is the connectivity, right? So the empirical formula just tells us the ratio. The molecular formula tells us the actual number and types of atoms. So there's other types of formulas as well. So yeah, that are called structural formulas. So a structural formula, and there's many different types of structural formulas actually, tells us how the atoms are bound to one another, right? And this comes back to your question. What if you have 2 molecules that have the same molecular formula, but that are connected differently? Those would actually be different compounds. Those are called isomers. You'll learn a lot more about isomers if you take organic chemistry. So the structural formula of water tells us that the oxygen has two hydrogens connected to it. Right? So it's HOH, not HHO. Right? This methane, which is the gas called natural gas, what you burn in your stove. Some of the buses say, natural gas. It's CH4. The CH4 doesn't tell you how the CH4 is put together. It just tells you that there's one carbon and four hydrogens. The structural formula starts to tell you how it's put together. There's a carbon, and the carbon is connected individually to four H atoms. The H atoms are not connected to one another. Same for the H2O2, right? The O's are connected, and each O is also connected to one H. There's these are very simple structural formulas. There's other types of structural formulas that have their own specific name. So perspective drawing, that starts to tell you what an element or what a molecule looks like in not just flat, but in 3 dimensions. Right? And so ball and stick models, space filling models, these, you're not really going to be drawing these, right? You might be drawing something like this by the end of the class. And definitely if you get into organic chemistry. These are typically computer generated, right? And these show not just the 3-dimensional shape, but also the relative sizes of the different atoms. So molecules, right? Again, different models, different ways to look at them. None of them are all right, none of them are all wrong. Each one is useful in its own way. Molecules, compounds, right? 2 types of compounds. What we call molecular compounds and what we call ionic compounds. So when we put, molecular compounds, this is kind of not a great way to define it, but molecular compounds are composed of molecules, which are, as we define, 2 or more tightly bound atoms that can behave as a single distinct object. Ionic compounds, on the other hand, are formed by the transfer of electrons from one atom to another, forming a pair of ions that are attracted to each other. And the thing with ionic compounds is that once you've transferred the electrons, we sometimes think about them as a distinct pair, but they actually, as we'll see down the road, form a big network. It's very hard to have a distinct object when you're thinking about an ionic compound. Right, so we saw things like water, carbon dioxide, methane. When we're talking about molecules, we're talking about what we didn't see is things like salt, right? Salt is an ionic compound. We'll see that very soon. Right now. So salt, table salt, is what's known as sodium chloride. And so sodium, the atomic number, if you look on the periodic table, you can't see it, but it's number 11 because that periodic table has really small atomic numbers. So it has 11 protons and 11 electrons. Chlorine, if you look over there, it has 35. It's atomic number of, 17, sorry. 17 protons and 17 electrons. And if it's an atom, it's neutral, right? This is what we talked about. But sodium is able to lose an electron. So if sodium loses an electron, now it has 11 protons and 10 electrons. It's no longer has a net charge of 0. It has a net charge of +1. It's no longer an atom. Now it's what we call an ion. It has a positive charge, a charge of +1. And because it has a positive charge, and because opposite charges attract, it's able to attract an ion that might have a negative charge. And so in sodium chloride, you have a chlorine atom, 17 plus, 17 minus, it's able to gain 1 electron. When it gains 1 electron, it has 17 protons, 18 electrons. Gains 1 electron, 18 electrons, 17 protons, net charge of -1. Right, so here you have a sodium plus ion, here you have a Cl minus ion, plus minus, they attract, and you form what's called an ionic compound, sodium chloride. Right, so sodium loses an electron to form a positively charged ion Na+, chlorine gains an electron to form a negatively charged ion Cl-. When you're gaining and losing electrons, or when you're forming ions, it's always by gaining or losing electrons, never protons. What happens if you change the protons? It's not the same element anymore, right? You change the identity of the atom. And so sodium chloride, here you have sodium in purple, chloride in green. Here, it looks like you just have like 1 and 1. But actually what happens is because these things are round, the charges distributed all around, you form these kind of lattices, networks, which when they're become kind of transferred to the macroscopic scale, become these crystals. Right? So salt forms crystals. Okay. And so this is going to be the last thing we see today. Positively charged ions are called cations, some common ones, right? Negatively charged ions are called anions. The positively charged ions, the cations, are just named for the element that they come from. So magnesium forms the magnesium cation. Aluminum forms the aluminum cation. Anions, on the other hand, they're negatively charged. They drop their, when you name them, they drop their ending and they gain the ending IDE, ide. So chlorine forms the chloride anion. Oxygen forms the oxide anion. What can you tell me about all these elements? What kind of elements are they? They're all metals. So metals form cations. What can you tell me about these? Nonmetals. Nonmetals form anions. Okay, so right around here is where we'll pick up on Thursday. Remember to